Welcome to Solar for Designers. This is going to be presented by me, Jeffrey Matthews. I'd like to keep this session interactive. Please shoot any questions you have. If I don't see them, or if I don't think they're relevant to that particular topic at the point, or if I feel I'm going to cover them later, I shall discuss them in the questions section also. So with the booming solar industry in mind, our latest course, Solar for Designers, showcases the design of solar PV systems while addressing the importance and fundamentals of solar by analyzing the practical aspects, promises, and challenges of solar energy. Some of our course objectives are: describe the importance and basics of solar energy, identify why renewable energy is important and solar energy's role, identify market drivers, understand how solar energy systems work, analyze solar case studies, and where the solar industry is headed. My name is Jeffrey Matthews. I hold a bachelor's degree in electrical engineering from the University of Houston. As a solar engineer and trainer, I've been involved in solar PV training and consulting. I have had hands-on experience in designing and implementing projects for residential and commercial entities, both domestically as well as internationally. I've played roles in solar advocacy groups here in San Antonio and Austin, and I participate in monthly meetings here to stay current with the changing industry, as it's ever dynamic. Every month there's something new. I've done workshops at the University of Houston for over 8 years now, training students in general and industry-specific skills related to solar. At GBRI, I found that my passion for teaching and sustainability came together, providing me a platform to promote sustainable practices to ensure a brighter and more sustainable future. So I would like to jump right in with one of the signature and landmark installations of our time. Gemma Solar is the first commercial solar plant in the world with central tower receivers and molten salt and heat storage technology. It has 19.9 megawatt power generating capacity, which translates into an expected net production of 110 gigawatts per year, and a 15-hour storage capacity in the absence of solar radiation, which is very unique. The tower is about 140 meters high, and its storage system allows it to produce electricity for 15 hours without sunlight, which is quite impressive. It all begins with the sun. The sun is the source of light and thus the source of life. It is mostly a gaseous body composed mostly of hydrogen with some helium and traces of heavier elements. The gases swirl and flow under the influence of gravity, magnetic fields, and heat energy. And it's a main sequence star, and thus generates its energy by nuclear fusion of hydrogen nuclei into heavier helium nucleus. In its core, the sun fuses 620 metric tons of hydrogen each second. Fusion is a nuclear reaction that combines the atoms of lighter elements into atoms of heavier elements, like we discussed. And this is one of the most powerful processes we know of in nature that can produce energy, which we've harnessed to manufacture such things as the hydrogen bombs. Cadmium telluride, this is made from cadmium and tellurium. As you can see here, they're flexible. You can see different forms of them over here. As a result of its physical properties, they have an optimum absorption profile for the light spectrum of sunshine. So it allows it to obtain better performance in dim lighting, more often than other applications. We should talk about some of the positives and negatives of it in a second. Let's start at the raw end of things. So you can have one of the many raw forms of this, or you can combine them to form polycrystalline or multicrystalline wafers. So first of all, we take it through the manufacturing process, which starts off with the crystal growth, and then we cut them into ingots. And if they're multicrystalline, there is multiple raw materials used. They're solidified together, and then we, based on a certain density, we doing the blocking, which separates them. And then it goes through inspection, cropping, edge chambering, wire saw, and finally we get these wafers. Really quickly, for those of you who are in the US, you have access to Renasola now. But these are the two primary panels that I would suggest to people. It's a very common question at the end of sessions. What are panels that you would suggest we use? Depends, of course, on the cost, availability. These are the ones that I use the most. So the one on the left is SunPower. That is the biggest name out of California. The reason why they're so sought after is their efficiency. They're 20% efficient. They have these E20 series, the E19 series, the E18 series, and these are some groundbreaking efficiency numbers. Of course, because they're produced in America, and of course because they're produced with such quality and high efficiency, they are also very expensive. They're about twice as expensive as Renasolas. Per watt, you would pay about $1.6, $1.7 for E90 for the E20 series. On the right hand, we have Renasola. These they're manufactured in Taiwan, if I'm not mistaken. They're high efficiency. They range from 15 to 18%. They cost about $0.7 or 70 cents, 80 cents a kilo per watt. When you compare the two, this is half as expensive, and the efficiency is just off by 2 or 3%, 3 or 4%. The SunPower is a lot more expensive, but a lot more efficient. So if areas are seen as constrained and cost is not, then you would go for SunPower.